Hey everybody, let's open with a word of prayer. Father, we're grateful. We try to be grateful. Sometimes it's hard to be grateful. Things happen that are not so pleasant, things that can even be evil, and it's because of that evil in the world that we despair at times. We grow weary of it, and we yearn for the time when it will be gone. Help us to persevere until that time, and to not let it overcome us, but help us to be the ones who overcome it. We pray in Jesus' name. Amen. Okay, we have a test coming up, and before we get to the test, which I'll be handing out on Monday, we need to cover one more topic, and that topic is circular motion. We've dealt with motion that is linear, right? Straight line motion, up, down, right, left, on inclined planes. We've dealt even with motion that is curved, throwing a football, trajectory problems, dropping a box out of an airplane, so we've worked on problems where we have one-dimensional motion, we have two-dimensional motion. Those are the trajectory problems. So we've had problems where we go right, left, up, down, on inclined planes. We've had 2D motion where we've had things that went like this in curved arcs. And now we're going to have 2D motion that is repetitive. Circular motion is repetitive motion. Now what we mean by that, unlike these other problems, repetitive motion, especially in circular motion, we start and we go in a circle, and then we get back to where we started, and then we trace our path again and again and again, and we go over the same territory again and again, at least in a simple circle, simple circular motion. And for that reason, it's repetitive. It traces out the same motion over and over again. Now, the fact that it's repetitive means that there are some different ways of talking about this motion than we've dealt with in the past. When we've talked about motion in the past, say these two up here, we've talked about the velocity. That's one of the things that we deal with when talking about motion, velocity. We've talked about acceleration, which is the change in velocity, right? The change in motion, either direction or speed. We have pretty much been limited to talking about motion in terms of those two, velocity and acceleration, and of course distance or position, right? If the position is changing, then there's motion. And those are all still going to be important things to talk about. But when we get to circular motion, because it's repetitive, let's say this was the position where we started the motion at the top. When I started drawing the circle, I started drawing it at the top. Because I go around the circle and I come back to where I started, there's a particular way of talking about this kind of motion. And the big idea is what's called the period of the motion. And that's just a fancy way of saying the time for one cycle, right? Because it's repetitive motion, it cycles, it repeats. So it's the time for one cycle or the time for one repeat. Well, a repeat, a cycle, a revolution. If it's circular motion, time for one revolution. These are all synonyms. These are all ways of talking about repetitive motion, and in this case, it's going to be circular motion. And to keep things a little bit more simple, we're going to limit our discussion to a particular kind of circular motion. It's called uniform circular motion. And uniform circular motion means the period doesn't change. Okay, we can have circular motion where the period changes. Something's going in a circle and it can go faster and faster and faster as it goes around the circle, and so the period would get smaller and smaller and smaller. Or we could have something that's going in a circle and it starts slowing down. It's still going in the circle, but it slows down. The period gets longer and longer and longer. That's more complicated. We're not going to deal with that. We could, but we're not going to. We're going to keep it simple. We're just going to talk about uniform circular motion where the period is constant. It doesn't change. And what that means there is a velocity associated with the motion that only changes direction but not length. Remember, velocity is a vector. It has two parts. It has a length and it has a direction. Well, obviously, as you're going around in a circle, the direction of the velocity changes. Otherwise, you couldn't go in a circle. But we're going to say that the length of the velocity vector, the speed, does not change. That's another way of saying uniform circular motion. Okay? Velocity changes direction only. Right, these are two different ways of saying uniform circular motion. The period doesn't change. The time it takes to go one cycle doesn't change. Or we can say, equivalently, the velocity vector associated with the motion has a constant length and it only changes direction. Well, there are a couple of things we know about velocity, and now we have a new thing called the period. And let me give you another little piece of information here. This is going to get confusing now. The letter that we use for period is capital T. Well, we've used that for tension in the past. So it was a vector and it was a force. Now we're going to use it as a scalar. Time is a scalar. It's not a vector. And it's going to stand for period. So you have to kind of be aware of the problems we're working on. Don't get confused. Every time you see capital T, it doesn't always mean tension. All right, here we're going to start using it, co-opting it for the use as period. Kind of standard terminology. T is the period. That's the letter we use in equations. And T equals time. Let's see here. We got something going on here. No, we're good. Equals time for one cycle. One cycle. Well, there's something else we know about one cycle of a circle. We know the distance for one cycle of a circle. Okay? The distance for one cycle of a circle is called the circumference. Circumference equals distance for one cycle. Okay? Well, that's very interesting, especially as we're now talking about velocity. Why? Because velocity equals distance over time. Right? The velocity of an object is how far it travels and how long it takes to travel that far. The ratio of those two numbers. It's also the slope of a position time graph. We've talked about it in other ways, but here's a simple way that we can talk about velocity, distance over time. Well, the velocity for circular motion then is 2 pi r, that's the radius of the circle. 2 pi r is the circumference, divided by the period t. That's an important equation. That's one you're going to have to know for the homework. The velocity of a circle, the velocity in circular motion, uniform circular motion, is the circumference divided by the period, 2 pi r over t. Okay? So if we're given the radius of a circular motion, you can use this equation. If we're given the diameter, you got to divide that by 2, and then it becomes, you can say pi d over t. I'm not going to give you all those equations. The idea is circumference over time. This is circumference divided by period. That's the idea behind the equation. Okay? All right. That's how fast the object is traveling as it goes around in a circle. Now, something going in a circle is accelerating because we said the velocity vector changes direction. So there must be acceleration, and there must be, therefore, a force, because Newton's second law still applies. Newton's second law still applies. F net equals m times a. And these are vectors. We've used this equation quite a bit now, for quite some time. And now we're going to apply it to circular motion. When we talk about circular motion, it becomes F centripetal. Centripetal force equals mass times A centripetal. And here's the idea. The only reason something travels in a circle is because there's a force pulling it towards the center of the circle. The only reason the Earth goes in a almost circular orbit around the Sun is because there's a gravitational force pulling the Earth towards the Sun. And there's a velocity trying to take me away from the Sun, and the two together create circular motion. If there was no force pulling the Earth towards the Sun, then the Earth would just go off into space. If there was no velocity, then the Earth would just go to the Sun and burn up. But if I have velocity trying to take me away from the Sun, and I have gravity trying to pull me towards the Sun, the two combine to create circular motion, or almost circular motion. Elliptical motion. We're not going to get into that. So that's why we call it centripetal. Okay? The acceleration, A centripetal, points toward the center of the circle. So we always know with a circle what the direction of the centripetal acceleration is. And it's a vector equation, so there must also be a force towards the center. Vector, vector. And we're only concerned with parts that point towards the center. So here's another little piece of information. First of all, A centripetal equals v squared over r. That's how we calculate the centripetal acceleration. If you check the units, you'll see it has the right units for acceleration, meters per second squared. And we can now calculate the acceleration using this kind of an equation, but it's only for uniform circular motion. When we know the velocity of the circular motion, v, and we divide it by the radius of the circle, that's the centripetal acceleration. The other thing we know is that F centripetal equals net force along the radius line. Okay, I'll talk about that here momentarily, but let me just get that out. The centripetal force, what we mean by centripetal force, it's a net force, which means we have to add up. If there's more than one force along the radius line, we got to add them up to get the centripetal. It's net. We've been doing net forces now for a long time. Here we're going to define a special net force, the net force along the radius line. Okay, that's centripetal force. And the other thing for circular motion is context. Context is always positive or plus towards the center. Since the acceleration is towards the center, that means we're going to define our positive direction as towards the center as well. Let's make some diagrams and show how this plays out, and then we'll do some problems. So let's say we have a circle. Let me get my tool here. Okay, there's a circle. Okay, and let's say we have an object that's spinning in a circle. So let's say that this is a ball on the end of a string. Okay, so here's the ball on the end of the string, here's the center, and here's the string. We'll make that red, string red. Okay, well, at the position where I've shown this with the ball at the bottom like this, and we're going to say that the velocity vector is that way. There's a relationship between the velocity and the radius. Here's the radius. The radius connects where the ball is located to the center. They're always perpendicular. In uniform circular motion, the radius line and the velocity vector are perpendicular to each other. Always, always, always. Okay. So here's a vector diagram. And let's say that we're swinging this ball up and down vertically. It's swinging up, and it's like you had the string in your hand and you were swinging the ball, and it was going in a circle in front of your body, up to your head, down towards your toes, and in a circle, vertical circle. Okay? So what are the forces on the ball? Well, we have the weight of the ball down, and in the diagram I've given you, there's obviously a tension. The string has a tension pulling up towards the center of the circle, up. And remember, this is not equilibrium. Not equilibrium. If we're circular motion, there is acceleration. There's centripetal acceleration. So these two don't cancel. There must be a net force. Okay? So we said towards the center is positive, so this is the positive y direction. So F centripetal equals T minus the weight in this diagram. Centripetal force is the net force along the radius line. Well, I have two vectors here along the radius line, the tension and the weight, and the centripetal force is T minus the weight, because I define positive as towards the center, that's up. So T is positive, weight is negative. Let's do another diagram. There we have our circle again. Oh, I don't want that. Okay. Let's put the ball up here at the top. Ball's at the top now. Here's the center. That's the radius. The velocity is now like this, change direction. Here's the vector diagram. Now my positive direction is down. Plus y is down, towards the center. My vectors are the weight down and the tension are both down. The tension, the string is still pulling down. Remember, strings can only pull, so it must be pulling down. Gravity is still pulling down. They're both in the positive direction. So we have here F centripetal equals T plus the weight, because they're both in the positive direction. Okay? And we're doing the net force along the x direction. Let's do another one. There's our circle. Let's put the ball over here, pulling towards the center. This is the radius. This is the velocity. Here we have positive direction is this way because that's the direction towards the center. We have the tension pulling towards the center, and we have the weight down. And here, F centripetal equals T. Only the T vector is along the radius line. The weight is not, so it does not contribute to the centripetal force. The centripetal force in this case is only T. F net along the radius line is the centripetal force. All right, last one, and then you should have the idea. There's our circle. There's the ball. There's the center. This is R. We have velocity is like this. We have this. Positive is now in, I should, nope, gonna make it. Rotated axes, positive x, tension is there, weight is straight down. Now we know the game. Make a box. This is weight y. This is weight x. F centripetal equals T minus weight x. Only T and the x component of the weight lie along the radius line. They are the only things that contribute to the centripetal force. My context is plus up towards the center in this case. So the T is positive, the weight is negative. Okay? All right, now, hopefully that gives you some idea about context and how we do our drawings. That's going to be very important for us. And then we want to do something else. Let me just mention this. Centripetal force. This is often a problem of conception. Okay, so here's the idea. centripetal force is not a special kind of force. It's not a new force. I mean, let's talk about the kind of forces we've dealt with so far. We've dealt with tension. We just did tension. We've dealt with gravity. We've dealt with friction. We've dealt with contact forces of pushing or pulling. Okay. We've dealt with normal forces. Those are all kind of fundamental types of forces. Centripetal force is not a fundamental kind of force. It's any of those that happens to lie along the radius line. I add up all of those. That's centripetal force. Centripetal force could be a normal force. Centripetal force could be a push or a pull. Centripetal force could be a tension. It could be gravity, like with the Earth. It could be a combination of any number of those if they happen to lie along the radius line. Centripetal force is just a net force. It's just a name we give to a special net force, and it can be any kind of force that happens to be in the problem. If the force lies along the radius line, then it's part of the centripetal force. Okay? So don't go looking for some new special kind of force. Oh, centripetal force is always some special thing. It can be any of the forces we've already talked about. Okay? All right, so let's solve some problems here. All right? So let's see. I think we're in chapter 10. I believe this is where we are. So let's open up to chapter 10. Yep, circular motion, uniform circular motion. I recommend reading some of the book. I mean, it's always good to look. There's a lot more here than I want you to be aware of. But let's just take a look at some simple problems, and then okay, so let's do an example. Let's look at example 10.6, 10.6, and that is on page 207, right? So we'll just pick this example out of the book. So here's what they say. We have figure 10.8, okay? We have a figure in the book, circle, and it says, assume that a 2 kilogram ball has a velocity of 5 meters per second when it rounds the top of a circle whose radius is 80 centimeters. So it tells us that the ball is at the top. It tells us that the radius, there's a tension, there's a string holding it, okay? And they tell us that R equals 80 centimeters, or 0.8 meters, put it in standard units, okay? We're going to have the mass of the ball is 2 kilograms, so the weight is going to be 2 times g little e, okay? And let's see, the velocity at the top is 5 meters per second, okay? Okay, and let's see. Let's make our diagram here for vectors. We have the weight down. We have the tension also down. Okay, those are our two forces, weight and tension. So F centripetal is tension plus the weight, okay? And we have our general equation, F centripetal equals mv squared over r, ma. F centripetal is ma centripetal, and a centripetal is v squared over r. So I've just combined those. This is kind of your general equation for uniform circular motion, mv squared over r. And we kind of know everything here. We know the m, we know the v, and we know the r. So I'm just going to calculate all that stuff. Okay, so let's see. We have the mass is 2. The v is 5. We're going to square that. It's 25. And then we got 0.8 meters, so 62.5. So F centripetal, 62.5 newtons. That's the centripetal force that's necessary to keep this object spinning in a circle at that velocity. Okay? And we know also that F centripetal equals T plus the weight. Well, the weight is the 9.807 times 2 is 19.614. 19.6. Right? So we can solve for T. Got this little equation here. See this? Nice little simple equation for T. T is going to equal the 62.5 minus the 19.6. 62.5, 42.9. That's the tension in the string. This is the tension in the string. This is how hard you're going to have to pull on the string to make this ball spin in a circle at that velocity and having that mass. Alright? Okay. Then they ask, what is the minimum speed at the top necessary to maintain circular motion? This is a typical kind of a question that gets asked. In other words, they want to say, I want to have the slowest speed. So now we're going to change the velocity and say what's the minimum speed that keeps it in this circle when the ball is at the top. Okay, so here's the idea. That means, another way to interpret that, so minimum speed and still stay in the circle means T equals 0. When they say minimum speed, think about this. If you're spinning a ball on a string and you want to make it go faster, you know that you've got to pull on the string harder. It gets harder and harder, and you could break the string if you try and spin too fast because the tension gets too high, the string will break. If you slow the ball down, you know that the tension gets less and less and less. Well, if you slow it down too much, the ball doesn't stay in the circle. There will go slack in the line, and it will not be in the same circle. It will be in a different circle. The radius of the circle will change. It won't be 80 centimeters anymore. It'll be less. Okay? Where will it stay in the circle but have the minimum speed? Well, when the tension just goes to 0. When it just goes to 0. Okay? Where the string is just still, it's still kind of stretched out at 80 centimeters, but there's no pull on the string when the ball is at the top. What does that mean? That means that the only centripetal force at the top becomes gravity, or the weight of the ball. So our equation at that point for minimum speed becomes F centripetal equals just the weight, which is the 19.6 newtons, and that has to equal mv squared over r, where now we don't know the v, and this is going to be v min. So I solve this equation for v min. So I would say v min equals, there must be a square root because it's squared, so it'll be 19.6 times r divided by m square root. Okay, so this is going to be the 19.6 times 0.8 divided by 2 and square root is 2.8 meters per second. Not meters per 8, meters per second. So V min is 2.8 meters per second. Okay? So there are a couple of, simple problems here. Hopefully that starts to make some sense. All right? Oh no. You gotta be kidding me. Okay, so let's see here. Let's do another problem. Okay, give some more examples here of how this works. Let me see. How about don't want to do that, don't want to do that. How about example okay, here's a good one. Let's take a look at example 10.4, okay, on page 202. All right, so take a look at that. It's basically a car going around a curve. Okay, so let's do this. Now, a curve, here's something you got to understand. Every curve is part of a circle. Now, you know, the curve in a road doesn't form a complete circle, but it's a piece of a circle. So while the car is going around the curve, it's traveling in a circular path. It doesn't go in a complete circle, but it goes in a circular path, right? So let's do this. Let's draw the curve. Okay, there's the curve. Here's the car, and it's going along at some velocity, right? Here's the center of the circle. Here's the radius, okay? And let's see the information they give us. What's the maximum speed that a car can negotiate a curve of radius 100 meters without sliding if the coefficient of static friction is 0.7? So here's the information. The coefficient of static friction is 0.7. And let's make sure that you understand something about static friction when you're dealing with cars and tires on the road. Yes, the tires and the road are moving relative to each other, but it's not kinetic friction. We don't use the kinetic friction coefficient. We use static. Static friction is when the hills and the valleys are locked together. And as long as a car isn't skidding, the hills and the valleys of the tire and the road lock together. The tire rolls over the road, but it's not sliding on the pavement. It's rolling on the pavement. That's different. Rolling is static friction forces. Skidding is sliding, and sliding is kinetic friction, where you're breaking the bond between the hills and the valleys. So we do use static friction here, and we want the fastest we can go, Vmax, without breaking the hills and the valleys of static friction. Okay, so here's the idea. Here's our context. Positive is this way, towards the center of the circle. We have F, S, max. Remember, static friction force max, right? We want to be going so fast that we have to use all of the friction force possible, FFS max, to keep the car on the road, okay? And there's no other force towards the center. It's just static friction force. That's the only force towards the center, all right? There's no gravity here because it's a horizontal road, okay? So the only force is the static friction force for a car on a horizontal curve. So we can say that F centripetal equals F static friction force max, and we know that that's mu static times the normal force. And I'm just going to make the claim that the normal force equals the weight, because the car is in equilibrium vertically and the normal force is vertical. Remember, it's the perpendicular force between the two objects interacting, the car and the road. And if the road is horizontal and the car is on top of the road, then there's a normal force up and there's the weight down, and the car never moves vertically, so it's in equilibrium. So the normal force equals the weight. And the weight is the mass of the car times g little e. Okay. So let's put all this together and see what we get. We get here's the general equation. General equation, F centripetal equals mv squared over r. Now what do we say? The r, we didn't put that down here. Let's put that down as a piece of information. This is a question, and r is 100 meters. Yes. Okay, so let's take a look at what we get. Here's our specific equation. The centripetal force is the coefficient of static friction times the normal force. Well, the normal force we said was m times g little e. That's the centripetal force. What I just wrote down, I'm putting this in brackets now. This is F centripetal equals mv squared over r. First thing to notice is that the m's cancel. I've got an m on both sides. That cancels. The mass of the car doesn't matter. That's a surprising thing. But it doesn't matter. So if I just rearrange this equation, I get mu s times g little e times r square root. That's the v. And that'll be v max. Right? There's the algebra. Okay? Here is the equation that will tell me the maximum velocity of a car on a horizontal road with a coefficient of static friction traveling the fastest it can go without skidding for the circle of radius r. Okay? Alright, so there's a problem. Here's another car on the road problem. This time we're going to use the diagram on page 203, where we have a car on an inclined plane. It's going around a circle, as you can see on page 203, but the road is banked. The road is banked, so the road looks like this. And the car is coming towards me, right? Here's the headlights, right? Here's the steering wheel, and there's the driver. Great. Okay, he's coming right at me, right? But this is just a view of the car coming at me. Here's the pitch of the road, theta. And the center of the circle is over here. Here's the center of the curve, okay? And the radius is this distance here. This is the radius, distance from the car to the center. Right? So that allows me to make my context. Right? So since the center line, the radius line, is my basis for F centripetal, that should be part of my context. And that'll be plus x. That's the positive direction towards the center. Here we have this situation. We have the weight down. We have the normal force up at an angle. Perpendicular to the surface of the road is the normal force. This is the angle theta there. Okay. And we know how to deal with this. There's no friction force here. This is the reason they bank roads in the first place, because you want to be able to have the car go around the corner without needing to depend on any friction. All right? So let's say we have this. This is the normal force x component, and this is the normal force y component. And in this case, F centripetal equals the normal force x component, and that's equal to the normal force times the cosine of theta. Cosine of theta? No, sine of theta. Sine of theta. This length of this side here is the same as this over here, and this is opposite theta, so that's sine. And so the centripetal force is the normal force times the sine of theta. Notice something else here. So here's our general equation. General equation for circular motion. F centripetal equals mv squared over r. Okay? Notice that the car does not move vertically. The car is in equilibrium vertically. Equilibrium vertical. So that means that the normal force y component must equal the weight. See these two vectors in the vertical? They must cancel each other. I have to have no net force in the vertical direction. So these two must be equal. So the normal force y must equal the weight. Right? So we also know from the trig the normal force y equals the normal force n times the cosine of theta. Now we got three equations to combine here. Okay, we've got this one here, trig for fny. We've got this equilibrium equation here. We've got actually four equations. We've got this equation for the x component of the normal force, which is also the centripetal force. And we've got our general equation for circular motion. Let's put all of these together, okay? So let's do this. Let's combine these two. The weight is m times g little e, and that's going to equal Fn times the cosine of theta. So the normal force is mass times g little e divided by the cosine of theta. Okay? There's one result. I'm going to kind of underline that. Okay? Then we're going to see, where does Fn come into another equation? Oh, comes in right up here. See it here? Let's stick this result in there. So we've got F centripetal is equal to Fn, which is m times g little e over the cosine of theta, times the sine of theta, times the sine of theta. And if you remember some trig, you'll know that m times g little e, sine over cosine is tangent theta. So I'm just going to simplify it, make it like that. So this equals F centripetal. Right, so there's another equation. And then I have my general equation, F centripetal equals mv squared over r. So F centripetal, which is m times g little e times the tangent of theta, equals mv squared over r. Okay? And let's see. Here's the way these problems typically go. Engineers want to know what angle to bank this curve. If they know the radius of the curve and they know how fast they want a car to go around it, like the speed limit, 55 miles an hour, and let's say it's 500 meters. So you know the R and you know the speed, but you don't know the angle. You're trying to solve for angle. So I solved this equation for angle. And look, the m's cancel again, cancel. And I get the tangent of theta equals v squared over g little e times r. And I can solve that for theta and say theta equals the inverse tangent of v squared over g little e times r. That would be the design angle for a banked curve on, say, a highway that wanted, they wanted to know how fast, if a car was going to go around at 55 or 60 miles an hour, what angle would they need to bank the curve so there would be no need for static friction. The car could go around without needing any static friction to stay in the curve, to go in the circle. Okay? All right. Now, here are some other things that we need to clear up in order for you to do the homework well. We talked about a couple of things related to velocity. And we said for circular motion, velocity is the circumference over the period, or 2 pi r over the period. Well, sometimes in problems, they can give you velocity information, but not in terms of meters per second. They can give it to you in other funny ways, like, here's a relationship that we're going to use later that you need to know now. F equals frequency equals number of cycles in 1 second or minute or hour. It depends on, frequency can be in terms of number of cycles per second, cycles per minute, or RPMs, revolutions per minute is another way of saying that, or cycles per hour, revolutions per hour. Okay, that's a frequency. So sometimes they give information about the speed of an object, not by telling you meters per second, but by telling you cycles in a certain amount of time. Revolutions per minute, RPMs. Cycles per second, which is a hertz. So let's just talk about some units here. Cycles per second equals a hertz. You've probably heard of hertz. That's frequency. Radio stations have a frequency 100.3 megahertz. Right? That's 100.3 million cycles per second. That's the frequency of the electromagnetic waves. So hertz is cycles per second, and RPM equals a revolution per minute, or a cycle per minute, right? Because a revolution and a cycle are the same thing, right? Sometimes in the problems in the homework you're going to see velocity information given in terms of a frequency. Well, you need to know how to convert that into a velocity that you can use in our general equation. So here's a relationship. Frequency is 1 cycle over the time for 1 cycle. Well, that's the period. So frequency is 1 over period. Frequency is 1 over period. And by the same token, period is 1 over frequency. That's the relationship between frequency and period. And then you can use period to calculate velocity, right? Because 2 pi r over the period is the velocity. So this is a way to get velocity information if they give it to you as a frequency, an RPM or a hertz. Okay? Some problems will do that, and you'll need to be able to convert from the information they give you to the information you need. And these are little equations that can be very helpful in that regard. Okay? All right. That should make you dangerous. Let me just make one more comment here about a particular homework problem. 1035 talks about an airplane diving and pulling out of a dive in a circular path, right? And they talk about a pilot needs to be able to experience 7 G's of acceleration. It's about the most acceleration, circular motion, circular acceleration that a pilot needs to be able to experience and not pass out. So there are tests for pilots to make sure that if they're exposed to an acceleration of 7 g's, they won't faint and lose control of the plane. 7 g's means what it says. It says that the centripetal acceleration is 7 times g little e. 7 times the acceleration due to gravity. That's what 7 g's means. So in these problems where it tells you about the acceleration due to gravity is 7 g's, because the plane is traveling in a circular arc as it pulls out of a dive, then you use those numbers. 7 times gravitational field, 9.807. Okay, to get numbers. Okay, to get numbers. And beyond that, I think you've got enough here to do most of these circular motion problems. Hopefully this is helpful. Test will be handed out next time we get together. Thanks everybody. Hope this is helpful for you.